Whoa, I even get to see Landon today. That's nice. How you doing, Landon?
Good.
Outstanding. Let's see, I gotta start off by showing you something cool. Let's do that right now. Share a screen. And it is time for Big Brother, a waterfall in Washington. And it illustrates today's discussion. So I want you to get a load of this. It is a beautiful place. White Salmon River. This is just a little video guy made of it. I'm gonna speed into him actually running it instead of being cool, but we're talking about impact and the hit that you take at the bottom of a waterfall like this today. Let's get up here a little bit to a good slow motion version of the better line you had. Doesn't that look fun? He's happy. Now I will show you what that same run looked like from his boat, from a head cam. This doesn't look like a good idea, does it? Yes. Boom. What do you think of that?
How do you know that there's no rocks to land on out there?
Because other suckers have gone first. Oh, that's quite a place, isn't it? Yes. That is the White Salmon in Washington. I've seen that drop with my eyes. It's a cool place. But ultimately, we're talking about today is impulse and momentum, and kind of you can appreciate. Obviously, he weighs a certain amount. He flies down through the air, but he's about to come to a pretty abrupt stop. And you can appreciate it's good that he landed in water as opposed to landing, say, on the concrete or something like that. And it turns out that the time it takes to come to a stop is kind of a big part of this, which is what airbags are all about. It's like, if you hit a wall, you're going to come to a stop. But if we can increase the amount of seconds, I mean, it's actually, tenths of seconds. If we can double the amount of time it takes you to come to a stop by you hitting an airbag, if you will, or in that case, hitting water, or even not even just hitting water, but landing flat in a kayak stops you way faster than if the boat actually lands at an angle, because then it kind of dips under the water. And so it takes more time to come to a stop. Well, your body likes that more. And so in the end, that's kind of what we're taking a look at today. So let me give you a little introduction to that. And again, what I'm really showing you today is actually kind of almost another set of formulas that accomplish the same thing that we accomplished before. Like you could argue, I don't really need this, which is kind of true and kind of not. So what we're going to look at now is in 15.2 in your book, 2 topics, which are actually the same thing as it turns out. Impulse and Momentum. Do you have any, either from physics or maybe just your own experience in life? Are those words you ever use? Like what does impulse mean? What does momentum mean? And again, I'm not looking for a textbook definition. Of course, you don't know that. I'm looking just for like, oh, that sounds like it means this. I mean, let's fumble around here for a minute. What do those mean? What does one of them mean? Volunteer yourself. Don't make me pick on you. All right, I'm picking on you, Landon.
All right, well, momentum a lot is we kind of use it colloquially a lot.
Yeah. Yeah, well,
Impulse.
can you use it in a sentence? Can you use momentum in a sentence? Can you think of it?
Yeah, like an example would be like, a heavy object moving fast, we typically think of having a lot of momentum behind it, essentially.
Yeah.
Outside of like a science fiction setting, I don't really hear impulse very much, though. You could, I don't know. I can think of like some impulse drives and like some high concept science fiction that shows up, but
yeah, impulse drive. I've heard that term too. And you think of like if a train is having a lot of momentum because it's like hard to stop, kind of that old hard to stop a train thing, even though it might just be moving really slow, it kind of has a lot of momentum to it. And really that's kind of what this all comes down to. So, and I want to see if this makes sense to you. Physicists have described or defined momentum as being mass times velocity. Why would it have mass and velocity involved? Even if you didn't multiply them, like why would momentum involve mass and velocity?
Heavy stuff's difficult to accelerate, and velocity stores energy.
Yeah, it's all about being heavy. Like, would you rather get hit by a train or a bullet? Think about that question.
None of
the bullet.
None of it.
You have to keep in mind that the bullet is in a smaller area, so you actually have like a higher pressure on impact, and then neither are ideal.
I don't mind getting hit by a bullet as long as its velocity is really slow, like my friend threw it at me. I got no problem with that. It has no momentum.
Yeah, I don't mind getting hit by a bullet as long as I don't get hit by a train.
But ultimately, a train has a lot of momentum because it's so massive. Like it doesn't have to be moving very much, and it can still kind of knock you. But basically, a slow train and a fast bullet could actually have the same momentum, and it's kind of like, stopping power, like what Daniel said about a bullet. Like it might sort of penetrate through you. But if you imagine getting hit by something hard, like it could knock you off your feet and be really small because it was coming in fast, or it could be big like a train and knock you off your feet, even though it was just barely passing by, because it just isn't going to notice you're there. I mean, if you're just standing there and you're close to the train tracks and there's like a handle sticking out and the handle hits you in the shoulder, like the train's not going to slow down appreciably, although it actually will theoretically. It's not going to slow down because of you. Now, the bullet that hit you, if you will slow down because of you. Like you'll fly to the ground just like the train made you fly to the ground, but you're going to change the bullet a lot. Like you're going to be able to change its momentum. And so that's kind of what this section's about. And so just the idea that an object's, I don't know, I like to think of this as kind of like, I don't know, this is my own language, just because it's kind of like a measurement of energy. And isn't that what we just studied the other day? It's kind of like it's just a way of measuring how powerful something is. I mean, again, it's all different words I could use. It's like a power measurement or something of that. Well, let's think about what the units for this would be. Let's see. Well, actually, let's talk about, let me write impulse in here first, or a second, because this relates actually to the kayak problem, because impulse is actually a force times a time. And that's what I was getting at before. So you're flying down to the water, and that impulse, and you might have a sort of a connotative understanding of impulse as it's being like quick. An impulse is quick, it isn't going to last over a long time. And so it's kind of a force and a time kind of put together. So in other words, that water might be putting a force of say 500 pounds on me as I hit it, because I'm hitting it with a certain amount of, well, momentum. I have a mass and a velocity that I'm hitting the ground at. And it's going to push me back for a period of time because it's going to bring me to a stop, right? It's going to bring me to a stop. It's going to have to counteract the momentum I have falling through the air, my mass and my velocity. And if I weigh less, I'm not going to have as much momentum hitting the water, which is actually good for me. But then there's going to be this impulse where the water kind of pushes back against me, and it'll be a certain amount of force over a certain period of time. And if that force is too big, like that can crush you, or you have internal organs that could separate, as a result of that, super hard hit, even if it was just just a hard hit. And so people have broken their backs off of waterfalls like that. That's a 25-footer. People have broken their backs off lower waterfalls than that. And so the sheer impulse, the sheer force over that brief period of time, bam, where you hit the water, your body just can't absorb that, if you will, if you're kind of, twisted the wrong way, or you're old, or, whatever the case may be. And so do you see how these are natural questions a person would be interested in, that, it's in the world that you're in here, physics, and, wanting to design airbags for cars and things that would actually kind of control this. And so as a kayaker, you have to learn how to soften the hit for things like that. Like, you don't want to fly, you want to land in that white water down below because it's really fluffy and soft, which basically means you'll kind of punch down through it a little bit deeper. And so it takes more time to slow you down, and therefore it won't have as much force against you that might break your bones, if you will. Or you can land, as I mentioned a minute ago, you can land with your nose down a little bit so that you actually kind of spear into the water, and maybe you go deeper. But again, that increases the time it takes to bring you to a stop. And if you can increase that, then you decrease the force that's involved. And so that's why this is kind of an issue. Well, let's think about what these units would be for both of these two new concepts. Well, mass is kilograms, and velocity is meters per second. And so there's momentum. It's kilograms times meters per second. So that's fine. And then force, let's see, force is newtons times time, but a newton is a kilogram meter per second squared, right? That's a newton. And then that's multiplied by time, which is in seconds. So what do you notice about those two units? Two different units for momentum and impulse.
They're the same.
They're exactly the same. Again, you got to write them carefully to show that, because one of them I could have made it look like Newton seconds, and the other would be kilogram meters per second, and then you would have just thought they were totally random, right? But they actually are the same thing if you expand out what a Newton actually is. And so these are the same concept. So just like other things that we've looked at, these are kind of conserving. And so in the end, what we're going to be looking at, and in this section, if I pull up our note sheet, look at chapter 15. So notice I have here impulse, which is obviously, or often abbreviated with an I, is force times a time, whereas momentum is a mass times a volume. And I pointed out here that they have the same exact units ultimately. And then what we're going to be looking at today is really kind of a formula that we've seen before. You know, we're back here, we had this kind of energy business where you had this initial energy, and then you added some work to it, and that would equal your final energy. And today is no different. Today is the exact same thing. It's, you have some initial, notice that little V0. You have some initial momentum, and then you have a certain impulse, or notice it says some because there could be more than one impulse acting on you. So you have a bunch of punches, if you will. And again, impulse kind of implies they're short. The time duration on these is usually really kind of quick. So I have a certain amount of momentum that I've got right now. Maybe I'm going down the road on my skateboard and I have a certain weight and a certain speed and I'm cruising down the road, but then something happens to you you hit a rock, a car hits you, a bird lands on your head, hits you in the face or whatever. You know, who knows what happens. There's like something happens to you that either makes you go faster or it makes you go slower. Think about a kid on a swing set. Kid on a swing set is swinging, and then you come in behind them and you add an impulse. Boom, you give them a push. And if you give it at the right time, that actually increases their momentum. They actually go faster because you're pushing right as they're leaving you. But of course, as the kid's swinging towards you and he's right at the bottom, if you give him a push right there, that's going to be pretty violent, right? His head's going to pop backwards and he's going to be unhappy. And so it depends what that impulse does, but the impulse is basically going to change your initial momentum, and the F is for final. Then you're going to have some kind of new final momentum as a result of that. So can you see how practical this is? I mean, you have a certain amount of energy, and then you sort of add something to it. And the note that I had here is kind of cool, is it's really similar to work and energy. It's just that we're talking about time instead of distance. So in the case of energy, it was a force times a distance. In other words, you have a force, and then how long are you, what's the distance you're going to push on it? Well, here it's a force, but it's like, how long are you going to push? How long are you going to do that? Now, I am curious because I haven't taken physics in so long. Did you study this in physics and, you know, forgot all of it? Or have you ever seen this before?
Yeah, we studied it before. I remember most of it, but I didn't want to just rattle off textbook definitions.
Yeah.
We had
I
a
mean, we
couple.
did a ton of momentum. I don't think we did impulse.
Mm-hmm.
I think I did it like a billion years ago in high school.
Yeah. Well, let's take a look at an example to kind of bring this to light. And what I want to do is play with this equation. I want to play with this equation right here a little bit with an example similar to what I've been describing. And we'll actually go do that kayak example in just a minute. But let's take a look at a baseball equation. So let me write this down. So our mass times our initial velocity plus the sum of any impulses we have. I'll write I for impulse, and those are forces times times. That's going to be equal to our final momentum. Okay, so let's think baseball. So how does baseball work? Well, you have this ball. Coached a lot of baseball. That's not a ball though. You have this ball coming in. Well, and let's give it some energy, some, speed. Well, what do you got for a baseball? Well, and again, I'll simplify the units for you, but I'll probably say this out loud. But I looked this up online, so like I have it right. Baseballs are 5 ounces, but I want to work in a metric just to make it easier. So we're going to say this thing has a mass of 0.15 kilograms. Because if I gave it 2 in ounces, then we'd have to convert and do all that stuff, and then you'd be a little distracted by the conversions. And so 5 ounces converts to about 0.15 kilograms. And so you got this baseball coming in. Well, that alone is not enough to determine what's going to happen, right? Because if somebody just tosses it underhand to you, it's just going to bounce off you. But if somebody throws a 100-mile-an-hour fastball at you and it hits you in the stomach, that's going to be different. And that's what this is getting at. The velocity is not enough. You also need to know the mass and velocity. And so let's give it a velocity. So let's say it comes in at 90 miles per hour. That's a respectable but not awesome pitch for a pro pitcher. But again, I'm going to switch that to 40 meters per second. That's what 90 miles an hour converts to. So now that ball is coming in with a certain amount of momentum. We got everything we need to know kind of about its energy. Now, of course, what we're trying to do then is hit that thing. And so, betraying my terrific algebra skills now, or my terrific drawing skills, I will now draw a bat. As with all of my art, I have to put a name on it that says that is a bat, in case you can't tell, because it's terrible. Now, do you agree that the bat also has energy? Like you're going to take a swing at this thing. And so, what about the bat? Well, let's give it, so we're saying it's kind of going whoosh, kind of go in that direction. The person's swinging it at it. And so we'll give that bat and we're going to make an impulse out of that. Notice it kind of doesn't make as much sense to to give this a momentum, because I could give it a weight and a velocity, but it's not being thrown. Does that make sense? Now, if I could throw one ball and have it hit another ball, and then it'd be like momentum versus momentum. But in this case, I'm going to give it an impulse. I'm going to give it a force. I'm going to give it a certain number of pounds of force, if you will, 5,000 pounds of force. I'm going to give it a force equal to 22,500 newtons. 5,000 pounds of force converts to that many newtons. And then how long do you think, what's your thoughts on this? How long do you think a bat is in contact with the ball? Because you agree it's going to be tiny. How much time are we going to give it? What's your guess?
Depends on how good our model wants to be.
Yeah, well, what's your guess in real life? Like this is meant to model a genuine major league swing and a hit. How much time do you think the bat is on the ball? I looked it up, so I'm going to tell you the answer, but what's your guess?
Tiny fraction of a second, even in real life.
Yeah, what I found online was 7 ten-thousandths of a second. I assume they figured that out with slow motion photography or something like that. I don't know, like we did the other day with the box sliding off the table. So this thing has a certain amount of momentum, but it's about to be paired with something that has a certain amount of impulse. And those are the same exact units. And so the question is like, what's going to happen as a result of this? What's the ball going to do as a result of this? Well, let's go plug junk in. So again, I think it's kind of cool to write the equation out and sort of write over the top of it with numbers so you can see everything. So this is all pertaining to the ball, not the bat. The bat is actually providing the impulse to it. Just like in the case of the kayaker, I'm not really interested in the water. I'm interested in the kayaker. I'm the one that's about to get my back broken. So it's like the water is going to provide the impulse, the push. So the ball, we know its mass, 0.15 kilograms. Because I didn't mess with any of the units, everything is in the right units right now. I don't need to write the units in this, although as I often say, I probably should be. And so the ball comes in at 40 meters per second. That's kind of its initial velocity, I guess you could say. But then, of course, it's going to hit this and then fly off in a final velocity in the other direction. So one of the things that's important about this problem, though, is that this is horizontal. In other words, I'm simplifying this to think of the ball as coming in horizontal, which it basically is. But we'll look at problems later where there's a horizontal and a vertical component, and we got to think about those separately. And then also it's horizontal and it's also directional. In other words, what direction is that force being applied? Does it make sense? It could be applied behind it, making the ball go faster, just like the kid on the swing set. The kid can be swinging towards you and you could provide a force in the opposite direction. It's going to be very different than if you turn around and take your same force and the kid's swinging this way, but then you come back and push that way. Now they're going to go faster, right? So in our case, our force is 22,500 newtons, but it's actually being pushed in the left direction, like the opposite direction. In other words, direction matters here. In this equation. So that, thanks to the picture, needs to be a negative number. And then the time, 0.0007 seconds. And the mass of the ball doesn't change. I suppose there'd be some examples in life where it would change a little bit. Maybe something is lost from that interaction. Part of it sticks to the bat, so to speak. But in this case, in a practical sense, not really. Notice what's cool about this. We're actually going to be able to know what the resulting, there's only one unknown left in this equation. We're going to be able to figure out the resulting final velocity. And just so that you can watch it happening, I take 0.15 times 40 I get 6. If I take a large number, negative 22,500, a huge amount of force, but a tiny amount of time, I get negative. This doesn't look right. Hmm. 22,500. I get negative 15.75. And so notice, if you will, the bat defeats the ball. In other words, there's more impulse energy, if you will. There's more impulse energy from the bat than there was from the momentum of the ball. So that means it's going to turn around and the velocity's going to go in the other direction. So I can see that now. It's not going to help it, if you will. And so the velocity final works out to be negative about 65. Maybe it's exactly, I can't remember. I just have the answer written down. Again, that doesn't speak to us too much, but just FYI, that's 145 miles an hour. So in the end, you sort of, as a batter, don't have any control over the time that the ball touches. In other words, it's just going to be a tiny amount of time, but you can do something about the force, right? You can lift some weights, carry a heavier bat. You can increase the force. And if you do that, the ball is going to fly out faster. And of course, faster equals further, and, you know, and maybe it's close to a fielder, but because you hit it faster than the next person, they didn't quite have time to get over to get it, and it went through into the outfield and you got a base hit. So that's kind of the idea behind the problems in this section, is just trying to figure out, you know, what's going to happen. A couple of things, a couple of ingredients get mixed together, momentum and impulse, and then you figure out what's going to happen kind of out on the other side, so to speak. Any comments on that, or thoughts or questions that in mind before we just do this again a little more realistically with the kayak example?
Is that still depending on where you're going to hit the ball?
Yeah, this is all kind of simplified by saying it's horizontal. In other words, if the bat was here, kind of stretched out towards you, that's not working, and you hit the ball kind of on the top of the bat, then it's going to fly up in the air. Does that make sense? And so I'm keeping it simple by keeping everything horizontal and not letting it jump out of that plane and have a vertical component. So I'm oversimplifying this just to give you something to kind of look at.
Yeah, there are a couple of things that are kind of bothering me here a little bit in terms of thinking about how to model it. Kind of my first thought would be assuming that the ball and the bat were both perfectly rigid.
Yeah.
Wouldn't the only the time that it takes for the impact to occur be like approaching zero? Pretty,
Yeah.
How would that actually work?
Yeah. So the whole concept of something deforming, I don't know if you've ever seen slow motion pictures of all kinds of sports, but like a golf club and a golf ball is an interesting one, because the golf ball is just sitting there, not moving at all. So it has no momentum, and then suddenly it's just impulsed with the golf club. But it's actually really interesting, because as the club hits it, the ball stays still and it kind of crushes, and then it sort of jumps off of the club, if you will. So you're exactly right. This is an oversimplification, treating the ball as though it's kind of not deforming against the bat and so forth. And you're right, that greatly complicates this. And so it kind of depends on what your application is. The same would be true from a car crash, right? Two cars don't just bounce off of each other without a dent. I mean, they cave into each other. And so that's going to kind of screw things up a bit, right? And so we are actually in the next section gonna talk about that. That's what impact. There's a topic in our syllabus called impact that actually deals with how much gets absorbed and so forth.
The other really big question I have here, just looking at the math side of this, is that if increasing the hardness of the objects that are coming into contact would decrease the amount of time they're in contact, would that mean that if you had potentially a softer baseball, would that baseball potentially travel at a greater speed?
My gut reaction was it would be the opposite, because it would deform against the bat, and some of that impact, if you will, some of that impulse would sort of be lost because it's smashing against it instead of just immediately, as you said, having to spring off. Because what it's doing is increasing the time that the bat is touching the ball. Does that make sense? Just like a airbag on a car would be. So they're touching for longer than 0.07. And you could appreciate that, you know, if I change this number to not 7/10,000ths, but 7,000ths, that's going to change the answer by a factor of 10. It's going to be 10 times, well, as you said, mathematically anyway, that's, let's see, am I right about that? Yeah, that's going to be 10 times smaller. So now this is like negative 1.575, if you will, instead of 15.75. And so,
Or actually, wouldn't it be in the other direction? Because it's F times T.
yeah, it gets smaller, right? So if I do 22,500 times a smaller number, then my answer is going to come out smaller.
Wouldn't it be a larger number though if it's a softer? Like, wouldn't be a softer substance be in contact longer?
You're correct. That's exactly right. Yeah, if it was, that time would be, the time would be longer. Yeah, no, that's right. It'd be longer, therefore bigger, right? So that'd be a bigger
Yeah.
number. Yeah, that's right. So it's a bit, I'm saying it backwards.
Uh-huh.
But yeah, it wouldn't be 1.57, it'd be 157. So yeah, interestingly, that would seem to indicate that now all of a sudden the velocity is going to be way more, which I agree kind of bothers me conceptually, just like you were saying. So yeah, I'm glad you brought that up. This is greatly complicated by kind of how they deform against each other.
Yeah, and I guess if you're thinking about it, you also, the force, it probably isn't going to be a constant amount anyway. Although I'm not sure how much that's really going to matter.
Well, to deepen this a little bit, let's play around with this a little bit more. So it turns out this is a 25-foot waterfall, as I mentioned out loud. And that's a picture of the same video you just saw, or it's same place anyway. Notice there's really nothing here. There's like no givens. Nothing's given. Let's just try to figure this whole thing out. Because I have run waterfalls and you get pounded when you hit the ground sometimes, when you hit the water down there, hit your head on the boat, and you know, it really feels like, man, I really took a hit right there. And so I'm curious about this. So let's try to make this as realistic as possible. So we know the person's falling 25 feet. Now, again, you might, if I was to pick on this a little bit, you might notice part of the falls right there is actually not a free fall. In other words, you're not just suddenly in midair and then you fall 25 feet. You're actually, you know, cruising downhill at an angle and curving. And so, you know, we have to oversimplify this to even get any kind of a rough idea. But let's say, okay, so let's give this person, well, our formulas involve masses and forces and times, right? So let's see what kind of unknowns could we throw into this? Well, I weigh 180 and my boat, I think, weighs 40. So let's give this kayaker a weight of 220 pounds. And you might think, okay, we have forces and we have masses. Well, that's a force. So that's a force, but not a mass. And so that's interesting. And so then we need times. Like, how are we going to get times? How are we going to figure out what's happening here time-wise? Well, we have some position formulas. Like, didn't we say that our position in y at an earlier time was equal to -1/2 times gravity, acceleration, times time squared, plus the initial velocity times time, plus the initial position? Like, that was our position equation. So this might give us something about time, right? Because it's like, how long is it going to take for us to fall down there? Because remember, when we're hitting the ground, what do we need? We need a mass and we need a velocity. Well, I know my weight, but I need a velocity. How fast am I flying? And so I'm really after a velocity here. So I've got that equation. Let's see what we can learn from that equation. Well, what things do I know? Let's throw in some things that we know. Like you could say, for instance, again, you can kind of set the axis wherever you want. But if you put the axis down here on the ground where the impact is happening, then you'd say your Y height is at, well, the finish position you're at will be at 0 when you hit the ground. So that's your position when you hit the ground. Your initial position then would be 25 feet in the air. Does that make sense? And we know the acceleration of gravity, at least in our system, is 32.2, and it's negative. And what would our initial velocity be if we're sort of sitting up here and we begin falling? Again, we're oversimplifying this, but if you're just sitting there, then you wouldn't have any initial velocity at all. In other words, nothing is particularly lifting you up or throwing you down from here. You're just sort of flying off level. And notice we're talking about Y, so you have velocity. That'd be horizontal velocity though. And so downward, I have none, assuming I just kind of went straight off it. Again, could we complicate this by saying, well, you actually start right there and that's only 20 feet. And because of the slope of the hill, you actually have some velocity and now it's at an angle. And then we got to figure out how much that is in each direction. And so we could make this a little more complicated. But notice that's kind of cool because that equation only has one unknown in it. So that middle term went away. -1/2. Actually, I already got the negative in there. I got the negative in this problem already, so I don't really need two negatives. So if I solve that for t, I get a time of, I get a time of 1.25 seconds. But again, that's you falling through the air, because what I'm trying to establish here is what's my velocity going to be down there? And the second equation that you know is the velocity equation, which is velocity final is equal to acceleration times time plus the initial velocity. That's how you get your final velocity. So if we were up at the top, again, with no initial velocity, but we now just learned that we were going to fly for 1.25 seconds under the gravitational pull of 32.2 feet per second, then we actually would know our final velocity. And again, I should say, just kind of, I said Y up above, but this is all vertical that we're working on here. We're just looking at vertically. So I get 40.25 feet per second for that. In the case of the pitcher a minute ago, we just had the pitcher throw the ball. It was like his arm is what caused this thing to get moving. But what's causing this to happen? Gravity. Gravity's pulling on you. And so I now know what I'm going to hit the ground with. So notice we can figure out then kind of my initial momentum. In other words, at the hit. I don't mean initial up at the top. I mean initial down at the bottom. Couldn't I say then that that is the mass times velocity, which we now know? But we just figured out that our velocity was, let's go the other way with that. Our velocity was 40.25. And what do we put in for mass? We don't put in 220. What do we put?
220 over 32.2.
Yeah, we got to convert it to a mass by dividing it by acceleration. So that's kind of annoying. So if I take 220 divided by 32.2 and then I multiply that by my 40.25 feet per second, I get 275. 275 what? What would the units of that be? Well, it's the same as a force times a time, so that'd be pound seconds. Speaking of that, if it's a force times a time, couldn't I have just taken 220 times 1.25 seconds and got the same answer? Force of 220 times the time of 1.25 seconds. Look at that. Also 275. That's kind of cool. That's the idea here. And that would have been easier, right? But again, I show you that just because it illustrates the fact that this is something we already know this. We've used this before. So if you will, that's how much momentum. Then you can appreciate what happens if you go off of, there's another waterfall I could show you called Palouse Falls, the world record for idiot kayakers now. I think it's 186 feet. This is 25 feet. The record is 7 times as high as that. So if you take that same 220 pounds, but then you fly through the air 3 times longer, does it make sense you're building up a lot more momentum? So that could be 3 times as big. It could be like 700 pound seconds, or a measurement of energy. That's a lot of energy. And now we're about to bring it to a stop, and this is going to determine whether we get hurt or not. Does that make sense? So that's kind of cool. So at impact then, so I've built up 275 for my initial momentum. My MV0 has been built up. And now I'm about to take a force times a time. A force times a time. And that's going to equal my mass times my final velocity. Now, sorry, I wrote initial. What's your final velocity? Reminder, we're talking about everything being vertical here. What's your vertical velocity? Kind of afterwards. It's nothing you have to figure out.
That's nothing, presumably.
That's right. You stopped. So this is nothing, therefore, because you came to a stop. And of course, that's going to happen in a brief second of time, right? Like right as you get near the water, you have 275 pound seconds of kind of energy or momentum built up. And now a force times the time is going to bring that to a stop. Now you might think the force is 220, but that's not the case. Just like the bat a minute ago, sort of the weight of the ball and the force of the bat are 2 different things. You just need to think of the river down there as being like, here comes something toward it and it's going to go, kind of push against it. So we actually don't know what that force is. How much time do you think? Now we got to make this up. We'd have to measure this watching a slow motion video or something with a timer on. How much time do you think it would take to stop that? We're going to make this up. Say, I don't know. What do you think?
Let's say a second because the math's super easy.
Yeah, let's keep it simple. Well, it's going to look maybe a little too boring at that. Let's at least give it something that changes the number. If we made it 1 second, then the force would match u. So say
Don't confuse easy with boring. It'd be plenty interesting with 1 second.
But the thing I'd like you to note about this is to Daniel's point, if we chose 1 second, does it make sense then the force that you applied, if you will, is the same as 275. So you're gonna have 275 pounds of force pushing on you. If I cut that time in half, what does that do to the force?
It doubles it.
Yeah, it's actually gonna double it. So now all of a sudden the forces are going up. You see why the airbag concept comes into play, or why you need to kind of increase how much time it takes you to come to a stop? So in this case, as I mentioned, down here, this water is really aerated, which is wonderful. It just means it's full of air. So it's going to kind of act like an airbag. And so you won't have to land any particular way to kind of be okay here. If you land flat, the flatter you land, the quicker you'll stop, as I pointed out before. But if you kind of jab in there straight, a little bit of an angle, then that'll take longer to come to a stop. So I'll just leave it at that since I wrote it down instead of erasing it. But if I solved that equation, I would end up with the force being, and notice that the units here, the units would all cancel out, and this force would be a force, which is pounds. That'll end up 550 pounds. But it is just interesting to note, if the time was, say, 0.2 seconds, that I'm really taking 275 times 5, then that force would actually be 1,375 pounds. Does it make sense that at some point you're going to have so much force there that you're going to get hurt as a result of that? That's why this is kind of a powerful concept. How much force can you endure? Well, it's only an impulse. It's only for 0.2 seconds. I can handle anything for 0.2 seconds. Well, your organs can't. So do you see why that tiny amount of time makes such a huge difference in these problems? Interesting. Just another side note. I won't resolve this thing, but remember the formula I showed you, that I guess I'll show you again really quick, said right here, the sum of all the impulses. Like there's more than one. Again, it's kind of hard to imagine there being more than one, but take a look at this. If we did this from the top, think about what the units of this would be. It'd be your mass times the initial velocity. We said the initial velocity was 0. But then what do you have from there? You have a force of 220 pounds times a time of 1.25 seconds. There's that impulse. And then there's the force upward times the time of 0.5 seconds. So there's two different forces, or two different impulses happening to you. One is gravity pulling you down, the force of gravity pulling you down for a period of time, and then the force of the water pushing you up. And then again, that's going to result in mass times final velocity. And because this is all vertical, your initial velocity was nothing and your final velocity is nothing. And so, you know, what happens in between? Like that ends up with the same answer. So there's more than one way to think about this. In a sense, what I just did right there is the easiest way possible. Notice I didn't even have to bring into play all of these sort of previous equations and so forth. Well, perhaps I did to get 1.25, right? Remember that time in seconds, we needed to figure that out. So maybe I did need to bring that involved, or I wouldn't have known the time. So that's just kind of cool to think about. I'll go ahead and write the same answer here just so that you can see that they're the same anyway. Let's see. Let's take a look at another problem that we did earlier, but just looking at it in light of these equations, this technique. Let's try to get this right based on impulse and momentum. So, and this is exactly the same problem I had before, but we're saying that if I draw kind of a free body diagram here, we're saying, okay, here's this kayak that has been reduced to a particle, as your book would call it, or just a point. It's being pulled on. And so what would the free body diagram for that look like? Well, you'd have the force that's pulling on it in this direction, since there's somebody attached to it, and we were told that's at a 38-degree angle. So there's that force. There's the weight of the boat itself pushing down on the ground. So I guess I'll call that the force of the kayak. But then there's the normal force, the force, I guess I'll call it force normal. Then there's the ground, which is pushing back against it. Force of pull, force of the kayak, force of normal. Is that it? Do we have everything? If you read the question, then you might see there's one thing missing that's realistic to be missing.
Force of friction.
Yeah, there's friction coefficient involved. So the problem would either have to say, you know, it's got wheels or something that takes friction away, but this is dragging through the grass. And so that means there's actually going to be a force due to friction kind of pulling back in that direction. So I got all these forces. And so we're used to seeing free body diagrams with forces kind of everywhere on them. And so, yeah, that's what impulse is really getting at is, so I've got, you know, units of force, I've got units of mass, I've got units of time. These are all things that I've got to consider in my set of equations. And velocity. And so that's what this is talking about. Like this person is trying to reach a speed. Notice it says reach a speed, which I guess is code for velocity final, isn't it? Like I want to know the final speed. And I've got a time here in order for that to take place. So that's kind of cool. And I know the kayak has a weight. I know its weight. That would make sense that I would know that. So what would the equation for this look like? Well, thanks to that pole being at kind of an angle, like all the other ones were horizontal or vertical, and I could kind of treat them separately. But basically, whenever, to overcomplicate it, or, you know, in most cases in life, it's a little more interesting than this. We've really got kind of two sets of problems to work out here. One of them is going to be horizontal. And one's going to be vertical. So let's see if we can figure out what the horizontal one would look like. Again, as always, I've got my mass times my initial velocity plus whatever force times I have. Perhaps I have more than one, I don't know. And that'll equal my mass times my final velocity. That's what's going to happen. But again, I'm only doing this under the guise of it being horizontal. So I could even put force horizontal in there or something like that. And these forces can only be horizontal. So what does that leave me to do? What do I know? What can I fill out? I'm gonna give you a second to stare at that. While I write out, I'm gonna write the same thing out for vertical. Well, a couple of things we want to add to this is, since we're talking about horizontal, does it make sense this is a velocity in X? And down here we're talking about vertical, so this is velocity in Y. Like I gotta distinguish that. And this velocity final would be in X, and this velocity final would be in Y. And these forces would be in X, and these forces would be in Y. So I got to think about that. So what do we know? Well, find the force he must pull to reach a speed of 12 meters a second. That isn't stated explicitly, but it kind of implies that you started out with no initial velocity. It wasn't already moving when you started pulling. I would want to make a test question more clear than that, because if you're told that he starts from rest, then it's kind of a clue that, you know, that that's there, but it's implied in this. This is kind of an open-ended problem. So I know that. And so let's see, okay, what forces do I have that are going in the X direction? Well, I've got a force of the pull, but it has to be modified by the cosine of 38 degrees in order to be horizontal. And I know that I'm going to be doing that for a total time of 8 seconds. But what about the force of friction? Well, there is a force of friction. This is why it says the sum of the impulses. So there's two impulses to this, the person pulling on it, but also friction pulling against it. So there's another one. So I gotta make room for that. Another force in X in a time. And so that's the same. Like it's still going to be 8 seconds. And I know I'm just filling in things that I know. I know I'm going to reach a speed of 12 meters per second. I know the mass of the boat is 32. So I've still got force of X, but that's kind of this force of friction. So I'm not super happy about this because it's got two unknowns. Do you agree with that? It's got the force of the pull and the force of friction. So I don't really like this equation. It's got two unknowns. But let's just leave that and think about it. Maybe this other equation will create two equations, two unknowns, or maybe there's something else I should know in that first one, but maybe you're not sure yet. So you just start filling in things that you know a little bit. So I'm assuming I'm going to end up with something similar happening this time. So let's move this over. I can see I have two forces up there now that are vertical. So that means I'm going to need a kind of a second set of these. So, okay, cool. What do I know? What do I know vertically? Well, vertically, this boat isn't moving vertically when it starts, and it actually isn't moving vertically when it ends. Do you agree with that? Because it's sort of staying level on the grass the whole time, so it's not moving up and down. So that's cool. That makes it a little simpler. The actual impulses that are happening to this are again happening over 8 seconds, and so both my times are still 8 seconds. So that's cool. But then I've got the force of the kayak pushing down. So I'll say negative force of the kayak. And then I've got the normal force pushing up. So that's positive. Do I know anything now? So I'm staring at this, looking at all of my kind of unknowns, and I'm thinking, well, that's not good. I see nothing in common, like they don't share anything. What do I know? What else can I do? Given that I know force is mass times acceleration. Well, I know the force of the kayak because the kayak is 32 kilograms and acceleration is not 32.2 because this is metric, but 9.81. So 32, and I could have filled this in on the free body diagram a long time ago. That's approximately 314 newtons. I'm just going to round it off to a whole number. It's 313.92. So that's kind of cool. And then I just also realized that there is one thing missing. What is missing from this? Looking at my free body diagram, what is missing from this?
Pulling force.
Yeah. There's a third impulse there that is acting on this thing that I didn't account for. So that's force of P. So also in the Y direction. So the force of the pull, and again, that's also for 8 seconds. Everything's happening for 8 seconds. So I've got the force of the pull, which is actually equal to, or actually the force of the pull times just the sine. Whatever the force of the pull is, which I don't know, times the sine of 38. So I just kind of have, stuff that I don't understand everywhere. I got lots of unknowns. I see unknowns kind of everywhere. And so the question is, can I fill some of those things in? So let's do that. So yeah, I just figured out that the force of the kayak could be replaced with negative 314. So the force of the kayak's pushing down. And what can you replace the force of friction with? What was our formula for that?
Point one times the normal force, which would be the y component of pulling force. So it would be the normal force from the weight of the kayak minus the y component of the pulling force.
That's exactly right. In other words, you take since force due to friction was equal to the normal force times the friction coefficient, then I could replace that with the normal force, which I guess I was calling force normal, times point. What was that, 0.1? What do I have for unknowns now? Where are we? Have we made too much of a mess of this? If I cleaned it up maybe just a hair, notice we're down to force normal and force of pull in the horizontal, and we're down to force of normal and force of pull in the vertical. So I was actually stuck with two equations, two unknowns. So it's actually going to take both of those equations to be able to solve this. So let's clean this up a little bit because it looks a little too messy to make sense of. So I'm going to write the horizontal equation. Let's see, I have 8 times the cosine of 38 times the force of the pull plus 8 times 0.1 or 0.8 times the force of normal And that's gonna have to equal 32 times 12, whatever that is, which is 384. So that's a little easier to look at. Is there any sign problems there? Are those all positives? Is there some negatives? Is that okay? The answer is no, so look a little harder.
Before 0.8.
Like this right here, isn't this force pulling to the right and this one pulling to the left? Does it matter that one is right, one is left? Yeah. What should I be changing up here then? In my horizontal equation?
Friction.
Yeah, one of those has got to be negative. You're actually free to define it the way you want, but we usually call things aiming to the right positive and aiming things to the left being negative. And so really that should be a negative, right? Any other problems? Is that okay now? I can't see any myself, so I will proceed. What about vertical? If I clean up my vertical equation, let's think about the directions up here real quick. Is that okay? So the force of the kayak was down, that's negative. I did have a negative sign here. That's good. Force normal is up, it's positive. Force of the pull is up. So I think I'm okay with signs on that one. So I have negative 314 times 8, whatever that is, which is negative 25, 12. And then I have 8 times force normal. And then I have 8 times the sine of 38 times the force of the pull, and that equals fortunately nothing. So that's a little easier to see. What do you do to solve that? You're an engineer. This isn't a math class. What are you going to do? What would you do to solve that?
Put it in a matrix on my calculator.
Matrix. That'd be my thought too. What about the rest of you?
You can probably use Desmos, no?
Yeah, Desmos would work too. You could graph these two things and let Desmos take over. So yeah, they both work good. I think I'll use Desmos just because I can show it to you a little bit easier. Let's see, I'm gonna lose this. I want to be able to look at it. So I'm gonna take a quick picture with my phone of these equations. The cool thing about Desmos too is it doesn't require near as much knowledge. And not only that, but you can just kind of type it in the way that you see it. You don't really have to do much to it. However, there is one problem here with Desmos, and you tell me if you can figure out what it is while I'm writing this. So let's see, 8 times the cosine. So I'm just writing out exactly what we just did. 8 times the cosine of 38 times force P. Let's see, I guess I'll just call it P. Can I call it P? I'll just call it Y. So force of P is Y minus 0.8 times the other force. I'm just going to call that X. Minus 0.8 times X equals 384. So where's my graph? Oh, there it is. Perhaps you're not surprised now that I put X's and Y's in to see that that's a line, because notice Y is not being squared. There's no squares, there's no logarithms. Cosine of 38 is just a number. Does anybody know what's wrong with this though? You have to know Desmos pretty well to know what's wrong with this. Why is
It's
this
probably in
not-
radians, right?
I think it's in radians. The little wrench up there, yeah, now I'm in degree mode. Did you notice it didn't change that much, but it changed enough it's gonna matter, so. Yeah, I'm in degree mode, so that matters. So what's my second equation that I just lost? Negative, again, it's so cool that I can just type exactly what it says and don't even have to mess with it. Negative 2512 plus the force normal, which was what I was calling X, so plus 8 times X plus 8 times the sine of 38. X plus 8 times the sine of 38 times y, and that is all got to equal 0. And so I am interested very much in that point right there. So yeah, graphing is really powerful, really cool. Engineers want to get stuff right. They don't get any bonus points for doing this in some other way. So let's bring that. And on a test, you're more than welcome to use any of that kind of cheatability that you have. So let's bring that picture in. Crop it down real quick. And let's see, let's make a note just so that it's clear that I let y be equal to the force of the pull, and I let x be equal to the force normal of the ground. By the way, I was very tempted back here to say that the force of the kayak and the force normal would be the same. Fortunately, I resisted that temptation. Why are they not going to be the same?
Because they're pulling up on them a little bit.
Yeah, you're helping. The pull upwards is actually helping that. So the force normal should be less than the force of the kayak if we get this question right. So since that's x, then we got the force of the normal. The force of normal we got was roughly 256 pounds. That's less than the kayak, because remember it was 341. Was this newtons, pounds? I forgot what our units were. Newtons, 341 newtons. And so sure enough, the force normal is less, and then the force of the pull, which was the whole point of this question, call it 93. How hard did you have to pull was this question. I said pounds, but I just got done saying it was metric, so I guess I should write that correctly. Newtons. So the whole question was just originally basically just find the force he has to pull to reach a speed in 8 seconds. Again, this is like work being done to something, except it was not work over a distance. It didn't say find the force he has to pull with to reach a speed of 12 meters per second in 10 meters. It was over a time. And so it's forces and velocities and times. So now I know how hard I have to pull on that over that time of 8 seconds, and then it'll be going the speed I want it to go based on friction, based on the weight of the boat. A lot going on there. So given what time it is right now, if you want some extra credit just to deepen your brain, could you get the same answers using the rectangular motion equations? Again, this is not new. We don't need to know anything different here to do this. But could you get the same exact answers by rectangular motion? And what I mean by that, just to remind you, is like the sum of the forces in y equals the mass times the acceleration in y. The sum of the forces in x equals mass times the acceleration in x. Could you blend your understanding of previous sections and actually get the same exact answer using that approach? And what numbers would you see? So the answer to that should be yes. And it's not as though It's not as though what we did today is suddenly like, oh, isn't that much better? It's just different. It's just it's another aspect of how you would measure something. Force and time, momentum, that's legit, I guess, based on the impacts that we had today. So I think we should stop there. So I think what we're gonna do, like, this is really just through 15.2. So we're still gonna be talking about the same concept, but in a more interesting context. And next time, and what we're gonna look at is things like, just to keep it kind of simple, it's like if this pool ball is rolling in that direction and it bounces into this one, in other words, it kind of eventually hits right there, then where do those go? Like, does this one go off in that direction? Does this one go off in that direction and that one goes off in that direction? Where does it go? How fast does it go? Because effectively, this one right here will have some initial momentum. It'll have a mass and a velocity. And then this one over here will have nothing. It'll just be sitting there. And then this bangs into it. And so what we're talking about is conservation of momentum, which means we knew how much momentum we had at the start, which was all kind of focused on this ball right here. But now that momentum is split into both of these balls, and one is going off in that direction and one's going off in the other. And so can we kind of figure out where they go and how fast are they going, that kind of a thing. That's just going to be taking what we've been studying to kind of another level. They bang into each other and off they go. So that's what we're going to do next. So you'll find that kind of fun. One of the first things I'll do next time is something called a ballistic pendulum, which is a kind of a cool way of determining what the muzzle velocity of a gun is. I wish there was some way we could actually go test this out and try it. I suppose we could. There's only 3 of us, but let me think about that. All right.
Before you head out, actually, I got a little curious about bats because it's kind of weird. So it depends a little bit on the type of the bat and whether or not if it's a baseball or a softball.
What'd you learn?
Well, I learned that interestingly, the metal bats actually store a lot of the energy and put it back into the ball. And it's kind of weirdly more of a harmonics question than it's a direct,
Momentum.
yeah, more the direct momentum question. And yeah, a huge portion of the energy is just bled off either into lost vibrations in a bat, especially for wooden bats, but also into into deformation of the ball. Surprisingly, not that much with a baseball, but a lot with a softball. And looking at like slow motion footage of it really shows it off because the baseball comes off the bat looking pretty much not deformed. But a softball, even after it leaves the bat, it's still really deformed.
Interesting. That's kind of cool.
Yeah, I found a really interesting. Well, I found this paper on it, and one of the authors of the paper has a website. It's been around since the early 2000s. It looks like it. It's just all about baseball bats and the physics of it all. So
I'm clicking on that link right now, but you're right. I mean, if you think about somebody holding like a aluminum bat, I played a lot of baseball. If you tried to push on it and deform it, that would obviously take a lot of energy to do that. So the idea that the ball deforms the bat and then comes back out, it's like that took energy and that's lost from the system. And so
no, actually, like the deformation of the bat isn't actually the loss of the deformation of the bat, or the no significant deformation in like an aluminum bat actually pushes back into the ball.
in other words, you get it back again.
Yeah, a lot of it. Yeah. It's really cool.
Yeah.
This is a lot more information than I expected to find so easily. But obviously, the modeling is a little bit hard because the especially when it comes to the deformation of the ball. It's a sphere and its composition isn't homogeneous. So it gets really, like, the best way to measure it is probably just experimentally. Anyway.
Right, there's a ton of links there. I'll just looking through quickly what you found there. That's what's so fun about this stuff, because a class like this is, I like that you're asking and thinking questions like that, because this class does not allow you to kind of leave here and then go design a safety system for a car. It's like there's a lot of extenuating circumstances, which is why I think ultimately the important thing in a class like this is to learn how to think. I mean, you want to be able to get some questions right and so forth and pass the class, but to notice, just like in the kayaking example, because it's the same with the boat, like the kayak hits the ground, the kayak is made of plastic and the bottom of it deforms too. And so that actually helps absorb the energy. And so to recognize there's a lot more going on. And, for the fact that people who really care about it, if you will, took it seriously enough to try to, include all the rest of that so they could really figure out what's going on, because they were interested in a particular topic. That's really interesting.
But yeah, I feel like the ugliest part of the kayak problem in terms of actually finding the time of the impact would be the water.
Right. You're so right. Even if you had time-lapse photography, how do you tell what's going on? It's like,
I mean, experimentally, you could put like what's it called, a potentiometer in the raft and probably find it that way. But actually calculating that, especially on the water side of things, it's really, really ugly.
well, yeah, we're also talking about such tiny times. It'd be one thing if it was somewhere between 21 and 21.5 seconds, because it wouldn't matter that much, but we're talking about tiny decimal places making a massive difference.
Yeah, I remember one of the really big engineering problems back in the day was accurately simulating water.
Yeah.
I mean, even now it's kind of a problem, but obviously computers help a lot more nowadays. But trying to remember what they were called. There were a couple of really big bay engineering projects where to actually test how the water would behave, they made scale models of it, just massive scale models. I'm trying to remember, there are a couple of really cool, basically giant facilities that are all about just simulating water in certain areas. I'm trying to remember the names of them more, but it's been a couple of years.
I read a book about a dam breach, and it was talking about water going through because the water was coming into the lake so high, they were afraid that it was going to overtop the dam, which is not something you want to let happen, because it starts eroding it and then the whole dam breaks and then you're really in trouble. So they have these other tunnels they're letting water through. But the problem is they were having to let so much water through that it was not flowing laminar. So laminar flow is where all the particles kind of flow in the same direction, and that's really fine. But if they start, I forget what the terminology is. I know laminar was linear type of flow, but then
Well, I want to say it's laminar and turbulent, I think.
you're right. It's turbulent. Yeah. If
It
starts behaving weird, then if the
Yeah.
water's motion starts to be, up and down instead of just left and right, well, now it's actually eroding the walls. And it was like they were hearing huge loud noises in the dam when this was happening, and they knew stuff was getting torn apart in there. And end result, when that water finally went down and, they got lucky and the dam didn't break, they went in there to look at it. And there's this huge concrete abutments just torn out and rebar ripped open. And it's like, how in the world can water do that? And so, yeah, that was the point of the book, was trying to understand how water behaves is actually still really difficult. It's not something we're very good at.
Yeah, even in just really relatively simple stuff like, basic, I guess not residential, but municipal plumbing. Just dealing with the fact that water is like pushing against things as it moves is kind of an issue. Like the actual like large concrete pipes we use a lot underground have to actually have supports in them to just kind of increase their surface area against the dirt to hold back the forces of the water trying to push the pipe apart, because they're not actually physically attached in any other way than they're just connected. So I thought that was really interesting.
Yeah, amazing, interesting.
I'm gonna say it really quick. Are you gonna have a time tomorrow to talk about the email you sent me?
Yeah.
Okay, because I thought we can talk right now, but I have to go to work.
Okay.
So what time are you going to be available tomorrow?
My class, I teach in the morning from 8 to 9, 9:30. So you could text me after 9:30 and we can hop on.
Okay. Okay.
I don't know a ton about that. I just got that email and I thought of you.
Mhm.
But I'd recommend looking into it. That'd be pretty interesting.
Okay. Okay. Well, I'd like to know more about it.
Yeah, let's figure it out together. Okay, let's talk
Sure.
tomorrow.
Right. Thank you.
All right.
Mhm.
See y'all. Good job. Have a good day.
See you, Doug.